In this video, I'm going to show you how to create and use a quad tree. Quad trees are frequently used in game development. Their most common use is for spatial partitioning. Spatial partitioning is a technique for dividing a game world into logical nodes. Quad trees, as the name implies, divide into four when split. The division of nodes allows for faster operations like finding nearby objects or culling a scene for visibility. Each node contains some kind of object. In our case, we'll fill them with game objects. This will allow us to find nearby game objects quickly and easily. Let's take a look at the code. Each quad tree is going to have a certain number of children, max object count, and a max depth. The maximum depth defines the maximum number of splits a quad tree can have. Each time a quad tree splits, a quad tree will add child nodes and set itself for the node parent on all of those child nodes. Further, quad trees at the root level are going to contain objects. The root level means quad trees that do not have any child nodes. Finally, each node will define a node center, node bound, and node size. Let's take a look at one of these in Unity. I'm using gizmos to draw the quad tree so we have something to look at, and it's easier to debug issues. Our quad tree interface defines a maximum node depth, a maximum number of objects per node, and the items to add is when adding items, how many we want to add at a time. The maximum node objects is a count that when the number of objects in a node goes over the maximum node objects, it will perform a split operation. And this is where the node will add those child nodes and add its own objects to all of its children. So let's look at adding some objects. Hitting the A key will add an object to our scene. You can see that 2, we are now at the maximum node object count. Adding a third will cause a split operation. So when this node split, it added 4 children, all at a quarter of the size, and then it went and added all of its objects to each of its children nodes. So now this larger node does not contain any objects, but only contains 4 children, 3 of which contain 1 object each. Further splitting will occur if adding multiple objects to an even smaller node, and will continue to go for another 8 levels down, which is the maximum node depth. Let's take a look at how these objects are added. Adding a game object to our quad tree, we'll test to see if the object is within the bounds of the quad tree. If it is, we're going to call this private method that's going to add the game object to our quad tree using the center of the game object as well. Add, taking an object and a center, is going to check to see if this node has any children. If it does, we're going to decide what child to put the object into. This is based on the object center and the node center. Depending if the object center is to the left or right, or above or below the node center, we're going to change the index of the child. With the object center being to the left of the node center and below the node center, will result in the index being 0 plus 0, meaning the index is 0. An object center to the right of the node center will be a 1 plus, if the object is below, it will be plus 0, meaning the index is 1. We recursively call this add call until we reach a child node that does not have any children. This is called a root node. The root node is where we want to place all of our objects. First, we test to see if adding the object is going to put us over our maximum object count. If it does, we're going to call a split operation. And for each object that we have, we're going to re-add it to our quad tree. This will add it to the child nodes that we've just created in the split operation. And finally, we're going to clear our list so that we don't have any objects anymore. This ensures that only root nodes have objects in them. Finally, we're going to add the object again that caused the split in the first place so that we can ensure we add it to the appropriate child node. If the object does not cause us to go over our maximum count, we're just going to add it to our objects. Let's take a look at this in Unity again. We can add multiple items at the same time in a random location here. So we can see when adding a large number of objects, the quad tree splits fairly evenly, with some spots having more nodes than others. And continuing to add objects causes deeper and deeper splits. So what's so beneficial about using this spatial partitioning? Well, when adding a large number of objects like this, like 1,000 of them, trying to find the nearest object to the point we click would require us to search through all of the objects in the scene and see which is closest. However, using a quad tree structure like this, we can split the scene and search fewer objects. For example, The nodes marked in red were those searched for the nearest node. The green line drawn shows us the node closest to where we click. This means we didn't have to calculate the distance to any of these other objects, and only the objects found in the red circles. This gives us a significant improvement in searching speed. In this video, I've shown you how to create and use a quadtree. The quadtree is a nice structure for many situations. The 2D nature of the quadtree can be a limitation, however, it doesn't limit you to a 2D world. Most games have a majority of their game objects in a relatively flat area. For example, a 3D real-time strategy game, the height of the world is significantly less than the length and the width. The quadtree we constructed here still accepts a third parameter. It's just ignored by the partitioning portion of the structure. However, it's still used to calculate the distance and find the nearest object. If we needed to also partition the vertical, we'd use an octree. I've included an example of this in a future video.